All right. Welcome back to 10, 418, 618. Structured prediction through the lens of graphical models and learning to search and deep learning. So in this course, we're going to be looking at all of these different sort of views of structured prediction, these different ways of conceptualizing what it means to do machine learning for structured data. But we need to start somewhere. And I would like us to actually start at one of the simplest places, which is classification. Okay. So before we get into those details, let's just do some quick Q&A, because last time we just kind of rushed through some syllabus highlights, and I didn't really give you guys a chance to throw questions at me. So any questions that came up from last time, just about how the course is structured, where we're going? Yeah.
For the team project, do we need to look for teammates by ourselves, or do you assign us for a team?
Oh, let's say that I've actually, let's say I'm undecided. So there's a lot of research that shows that if I randomly assign teams, you all will learn better. There's something about, like, you do a team with your friends, and I don't know exactly what goes wrong, but something. And so the team formation isn't going to happen until much later in the semester. So let's say it's undecided for the moment. But I'm happy to, either way, we're going to be happy to help form teams. So, okay, so this one I had to pose as a question that you might ask, because I actually had it wrong on Piazza. So I figured this all out back in July, and what we really want you to do to join the online section is email Dorothy Holland Minkley at this email address, stating that you would like to join the online section. And part of the reason for that is this is not professional video recorded, and so for anyone who decides to join this online section, we want to make sure that you know what you're getting into, and so hence the extra step. Okay, so another question: will I get off the wait list? Don't be on the wait list. Just email Dorothy and get on the online section instead. I think that's actually the best solution. And then another question: can I move between 10.418 and 6.18? So yes, I think this is extremely easy. Just email Dorothy. Basically, if you're catching on, I can't actually do anything for you, but Dorothy has incredible superpowers. So this one, I don't have an answer for. When is the last possible moment that you can move between 418 and 618? Still trying to figure that out, but I'll get back to you on Piazza. Okay, so I want to pose one more question that you could have asked, which is, so why is it that these interactions appear between variables in this Wikipedia info box example? I think just from some of your questions after class, I was realizing that I think what I was saying wasn't entirely clear. And I think I put my finger on what I was thinking about in this problem that you might not have been, which is that I was thinking about the test time setting. So specifically, at test time, an author writes a new article. We'll call that a vector X. And the info box is completely empty. And so a machine learning system has to populate all the fields at once. That's our vector Y. And so there were interactions that were seen among those random variables representing those different fields in a Wikipedia info box at training time. And those are unobserved at test time. And so the point is that we want to model what those interactions are. We want to learn about how those random variables are interacting with each other, such that when we go to populate a completely empty Wikipedia info box, we're able to simultaneously reason about multiple fields at once. So that is really critically, I think we kind of had some questions around this notion of whether the interactions are happening between sort of observed and unobserved variables. And critically, this is a setting where you can have fully unobserved fields. Okay, any other last questions? Okay, so we left off in our discussion of content last time at this notion of a roadmap for this course. And so I guess there's this question, which is, today we're going to be talking about classification. So how do we get from classification to structured prediction? Well, we're purposefully starting here with the simplest possible setting where you could think about decomposing a problem into something smaller. And then we're actually going to formulate structured prediction as a search problem. And there we'll be thinking about how you can treat the actual structured prediction problem by decomposing it into a sequence of decisions that you make. And then after that, so that'll roughly be the content of next lecture. After that, or maybe the next 2 lectures really, because we'll also be kind of talking about this in the context of deep learning, and so we'll be building up some tools in our toolbox there. Then we'll actually start to get to the framework of graphical models. And so I think that this is actually a great way to get where we're going. And so graphical models are about decomposition into parts. And so, we could think about what it's like to have a joint distribution over many variables. If you have a sentence, time flies like an arrow, and you're trying to predict what its part of speech tags are, one way would be to draw samples from some joint distribution. Now, did anybody bring a distribution over part of speech tags for this sentence? No? No one? Oh, okay. I happen to have one. So here is the first sample. Okay. And here's another sample. Oh. And here's the third, and the fourth, and the fifth, and the sixth. Okay, so conveniently, I have this ability to sample from distributions over part of speech tags for this sentence. And once we've done that, we could actually do interesting things. If you had enough samples, you could actually say that an approximation to the marginal distribution of this random variable is given by the actual observations that we've sampled. So we could say that about 2/6 of the time it's verb, and 4/6 of the time it's noun. Okay. If we had enough samples, we could count how many times each sample appears. And we could say that the one that appears the most times is the most probable assignment to these tags. Okay. We would need a lot of samples to pull that off, though. There's lots of different sort of joint distributions over multiple random variables that we could have. And the graphical model is actually going to tell us what interactions between those variables we are capable of modeling and learning. And that's what these different connections between those circles, which are random variables, are. So we could draw many samples from a distribution over, say, 6 random variables like this. And you'll notice here that their connections, their topology in this graphical model look quite different. Okay. And so we could also say that the graphical model is itself a joint distribution over both tags and words. And so in that case, our joint samples from that distribution would look like pairs of tags and words. And so a probability distribution here could actually tell us something about the probability of the sample flies fly with their wings. Okay. And so what we're actually looking at here, and this is just sort of a preview of what's to come, are factors. And these little black boxes, each one is going to look at the values of its neighboring random variables. And it's going to have an opinion about how much it likes or dislikes them. Okay, so it'll look at some of, so this factor here is going to look at the pair x2, x3. And if they're a good pair, like say a determiner followed by a noun, then it'll be happy. But if it's something a little more unusual, like a determiner followed by a determiner, it'll be somewhat sad. Okay, and so we actually draw these little things as squares because conceptually we're going to be thinking about them as tensors or unnormalized distributions over tags. Okay. And we're going to actually sort of choose to reuse factors, and this will sort of lead to a discussion of parameter type. Okay. And so if we wanted to specify a joint distribution using a factor graph like this, what we would do is actually sort of pick out the entries in these factors that correspond to the variable assignments that we're concerned with. And then we would multiply them all together. Okay, but there's a problem there, which is that if we just multiply these numbers together, we get something that's greater than 1. Okay, so what we do is we add in this factor, which is 1 over z, where z is what's called the partition function. And it makes sure that the normalization works out. Okay, so if we had this joint distribution over tags and words with these factors that could take on arbitrary positive values, then we would call this a Markov random field. Okay, and the factors aren't necessarily probabilities. But if we made the factors so that they were locally normalized probability distributions, then we'd actually have what's called a hidden Markov model, just a slightly different model. And so you can see that the hidden Markov model doesn't actually need the partition function, or we could say that the partition function is always 1 for a locally normalized model. This is also called a Bayesian network. A hidden Markov model is a special case of it. Okay. And then a conditional random field is going to specialize each of these little factors that was touching one of the words and say that it's now specific to a word. So it's kind of like we took a column out of the Markov random field specific to that word. So here we're going to take this column corresponding to time, and we'll get rid of all of the other columns. And then here we'll keep the column corresponding to flies and get rid of the others. Okay. And so this will give us a different distribution, a conditional one, which is now the probability of the tags given the words. No longer is it a joint distribution over the two. Okay. So samples from this distribution would just be a sequence of tags.
Exactly, what is the partition function a function of?
Oh, it's actually, it depends. So in the Markov random field case, it's actually just a constant. But in the conditional random field case, we'll talk about this more later, it's actually a function of x, the thing that you're conditioning on. So in this case, it'll be a function of the sentence, time flies like an arrow. So if we talk about the partition function that shows up in logistic regression, that's also just a function of x. It's the constant that makes sure that logistic regression sums to 1. Okay. Okay, so this is where we're going. Okay, that's like the 5-minute hand-wavy preview of like the kinds of models that we'll be able to talk about once we get to graphical models. We're not there yet. Today, I want to do something simpler. Binary classification. Except we've all talked about binary classification before. There's like these linear models, and you have some red points and some blue points, and you want to find some hyperplane that separates them in high-dimensional space. And so you try to actually learn that hyperplane. And once you've learned it, then you just have this nice, easy prediction function which looks at the parameters of the hyperplane theta, takes its dot product with your feature vector x, and says that we're just going to return the sign, plus or minus 1, of that dot product. Okay. And this shows up all over the place, right? Perceptron, logistic regression, naive Bayes, SVMs, many more. If we wanted to do Perceptron, it's usually talked about as an online algorithm where we have this stream of examples coming through, and the predictions are that same sign of theta transpose x. And then learning is this iterative procedure where we get an example that shows up one at a time. We make our prediction with it, and then if we've made a positive mistake, we add the feature vector. If we've made a negative mistake, we subtract it. Okay, so binary logistic regression, it looks kind of similar. We have these data points that are xy pairs. So the x's are these continuous vectors of length m, and the y's are maybe not plus 1, minus 1, but by convention 0 and 1 for binary logistic regression. And the model that we all hopefully know here is, that the probability of y equaling 1 is just the sigmoid function applied to theta transpose x. Okay. And then learning is just a matter of maximizing the likelihood of the data. We do that with things like gradient descent or stochastic gradient descent. And then we predict by outputting the most probable class. Okay. And we could talk about SVMs, and we'll actually come back to SVMs later on. Here's just sort of the usual formulations of binary support vector machines, right? So we have a hard margin version that assumes that the data is linearly separable. We have a soft margin version that adds these slack variables so that we can actually account for non-separable data. We could take the dual of these so that we can come up with more efficient algorithms for learning. And of course, there's always decision trees. You can have a binary classifier out of a decision tree, though it's easy enough to get a multi-class classifier there as well. Okay, so we know this setting, right? Supervised learning, we have these pairs of training examples. Binary classification is going to be this +1, -1 labeling. Multi-class classification, which is where we're going today, is going to be this labeling from 1 to k, where k is the number of possible classes that we could consider. Okay, so are we all kind of familiar with all this stuff? I know it was a long summer, maybe you haven't seen this too recently, but hopefully this stuff is all not too far gone in your memory, right? Okay, so what are we doing today? Well, today what we want to do is we want to think about how we could reduce the problem of multi-class classification to binary classification. Okay, and we're going to look at that. We're going to look at 4 different such reductions: one versus all versus all, classification trees, and error-correcting output codes. Actually, just by a quick show of hands, how many of you have seen any of these before? So how many of you have seen one of these reductions? Okay, great. Maybe half. And where have you seen them?
SVM, when you have utters,
Yep.
SVM applied to multi-class.
Yep, exactly. Great. And then let's do it more fine-grained. So how many of you have seen one versus all? All versus all? Classification trees? And error-correcting output codes? What would it be? Okay. And then we're also going to talk about multi-class classification, hierarchical classification, and extreme classification. How many people know hierarchical classification or have thought about that before? And extreme classification? Okay, great. So multi-class is like the simplest possible structured prediction setting. And so the key insight is that we're going to find these sort of simple ideas in these reductions that are analogous to the sort of later, less simple concepts that we'll be talking about. Okay, so for those of you who have seen these before, you can nod along, and but it'll also help us, even if you have seen them before, to start to establish some shared terminology and notation. Okay, so to jump in, we want to talk about reductions of multi-class to binary, and to do that, I want to paint a picture of the actual setting that we're working under, which is a sort of funny setting. And if you have never thought about this before, the first question that you should be asking yourself is, why on earth would we care about reductions of multi-class classification to binary? And so part of the reason is a historical one, which is that there's this sort of past setting that existed that came up because there were a lot of binary classification algorithms out there. And so what we're going to do today is we're going to suppose that you're given 2 things. One, a binary classification algorithm. Okay. And then that's going to look like sort of 2 things. We're going to say that we have some function called train that takes in our data set D and gives back some theta. Okay, and then we're also going to assume that we have something that gives us a y hat, which is given by some h theta of x. Okay. And then we're also going to assume that we have a multi-class classification problem. And that problem is going to consist of a data set D that consists of pairs xi, yi, where we assume that each of these xi's is a real valued vector of length m, and each of these yi's is a integer label from 1 to k. And so what we're going to be assuming here is that that we're really solving the multi-class problem. And so, we could say that for k equals, say, 3 and m equals 2, we might have a problem that just looks like, say, 3 circle points and maybe 4 plus points and a couple triangles. And our goal is to actually learn how to separate them out. Okay, so the first reduction that I want to look at is that of one versus all. So this is reduction 1. And we're going to say that the way this works is pretty simple, actually. So the key idea here is that we're going to train k binary classifiers, and each one is going to actually distinguish one label from all the others. So this is a pretty simple idea. And we'll actually predict by voting. Okay, so what do we actually need here? Well, for one, we need an assumption. So here we're going to assume that each class is actually separable from all the others. And armed with that assumption, we can now come up with a training and prediction procedure. Okay, so training here is going to be that we're given our data set D, and then we're going to iterate through each of our possible labels. So this will be for L in 1 up to K. We're going to say that we're going to define some data set D that consists of all of the, some data set DL that consists of pairs xi and let's say zi subscript L. And it's going to have the size n sub L, which is the number of, n here. And so this data set is going to be the same size as our original data set. And the question is, what do these z's look like? So we want the positive examples to be all of the cases where the true label is L, and the negative examples to be all of the other examples. Okay, so we could just say that ZIL here is +1 if yi equals L and -1 otherwise. Okay, so now for every label, we have this data set that actually divvies everything up into whether it has that label or it does not. And from there, we can just learn a set of parameters, we can call them theta L, which are going to be what we get when we train our binary classifier on this data set. Okay, so what is that function train? That function train is just what we assumed that we were given in that binary classification algorithm, right? So, okay, so far so good. What should we do when predicting? Okay, so assume that you're given a new instance, and we'll call that instance X. And the question is, what do we do? How do we actually come up with a label for that instance X? Any ideas?
Use a combination of the previously trained.
Yeah, so how should we combine them? Any thoughts? Well, I know you've seen it before, so you raised your hand on it. So let's see if, do you have another idea?
Well, I guess if you run your training example through this, and then for every instance that shows a positive, you somehow like figure out a way to break the tie between all the positive examples if it is a null.
Yeah, so if we ran, we could even say that we're going to do something like a for loop over all the L labels in 1 up to K. And so for each one, we're going to say come back with a score sub L. Okay, let's just call it S sub L. And S sub L is going to be the output of the classifier, right? H theta of X, right? And so then we could return, say, the argmax over all possible labels, L, in 1 up to K, of those S sub L's that we just computed. Okay, and then the key caveat here is that we're going to have ties. Boy, ties are annoying. So let's just break ties randomly. Okay. This has some convenient theoretical properties, which is, it makes proving a little theorem a lot easier. But it's not a particularly good idea. Question?
So isn't S sub L is only plus 1 or minus 1?
That's right.
So like okay.
So it's really just looking at, so if S sub L is just plus 1 or minus 1, I mean, we're really just taking, which of these classifiers actually said yes. And there's going to be a lot of ties. So let's actually look at this pictorially, because when you see the picture, suddenly this seems like kind of a ridiculous thing to do. Okay, so and I'd actually prefer that you think it's ridiculous. So this is going to be 1 versus all with m equals 2. So we have 2 features. We have 3 classes, and our binary classifier we're going to assume is a linear model. Okay, so that just means that y is, say, going to get the label plus 1. So in a linear model, when does it get plus 1?
Logit is greater than 0.
But we don't even need to talk, or well, yeah, so what is the logit?
The dot product between feature and weights.
Yeah, exactly. So we're just going to have, so something like W transpose X plus a bias, and if it's greater than 0, we return plus 1. And then we just return minus 1 for X. Okay, so what this means is now we could actually draw some pictures, because we could think about this as essentially, oops, it's not going to work for me. So we're going to have some data set where, as before, we have some blue points up here and some red points down there. and some green points over here. Okay. And the first thing that we're going to do is we're going to say, okay, well, we're going to create our blue data set. So let's call that D sub B for blue. And it's going to have the blue points up here, but then it's going to have so these are going to be our plus points. So we should probably show them as pluses. So we have these blue pluses, 1, 2, 3, and then all of the other points, these 3 red points, those are minuses, and these 3 green points, those are minuses. Okay, so when we actually train our classifier here, what do we get back but a linear model that looks something like this? Okay, so far so good. Now we can do this 2 more times, once for the red points to get the red data set, where now we have 3 pluses here, and then minuses everywhere else, that we had green and blue points. And so when we train our classifier, again, we get something like this. And lastly, we'll have our green data set, and here we'll have our plus points in this corner, and our minus points everywhere else. Oops. And we'll learn some linear model that looks like this. Okay, so when we put these all together, what do we actually get back? Well, we get back, so let's actually now combine these back on that original picture of the data set. Okay, so we're going to have one linear model here, we're going to have another linear model here, and a third linear model for the bottom corner. Okay, so what portion of this should I actually shade as blue? What is our classifier going to classify? Which points are going to be classified as blue? Which ones?
The region above the blue line.
So the whole region? There it is.
Is the one which is not crossing red.
Yeah, it's actually going to be bounded by, let's see if we can get this to look right. It's going to be bounded by that red and that green. Because only in that region do we have 2 minus 1s from the red and green classifier and a plus 1 from the blue. And then similarly, only this region is going to be categorized as green, and only this region is going to be categorized as red. And everywhere else, so in here, in here, in here, and in here, all of these are going to have ties, 2-way or 3-way ties. 3-way in the middle, right? And so what we get is sort of something a little bit disappointing. Because now we don't even know how to properly classify in those regions. Okay, so how could you fix this? Someone else. Yeah.
Well, if you have k minus 1, there will be no class.
If you have k minus 1,
Classifiers.
k minus
They
1,
just pick the last one. If it's all negative, it's the last class.
I don't think I'm following what your idea is. So you're saying we have 3 classes here. So
Right.
you're saying we have 2 classifiers.
Right.
And so in that case, we would never have ties?
Yeah.
Well, I don't know if I agree with you, because so here, if we just have the red and the blue classifier, they're still gonna be regions where they both say yes or they both say no. You could construct them so that they did not ever have ties, but they don't know about each other. Remember this step up here? When we trained this thing, in step 2, we said that theta L is just from some training algorithm that just gets to look at one binary data set. It doesn't get to look at the other classifiers. Okay, so can anyone try to fix this?
If an instance falls in the random area, maybe we can calculate the distance between this data and each line, like blue line, green line. and choose like the nearest one.
Great. So what we could do is to actually fix this, we could say use scores instead of sort of just +1, -1. Right? So in particular, does this look kind of like any other algorithms that you know?
Logistic regression.
Yeah, it looks just like multinomial logistic regression, right? So the connection there is that multinomial logistic regression is instead sort of defining something like, we could say that h theta of x is, you know, the actual probability or the score according to your model, right? And then in multinomial logistic regression, it's pitting against each other these different probabilities from these three different hyperplanes. And as well, sort of the bad part of this one versus all thing is that training does not calibrate the parameters across the different classes. So when you're training one versus all, the one classifier doesn't know anything about the other classifier. And so the scale of the parameters might actually be totally different in one classifier versus another. And so if you aren't using probabilities, if you're just using scores, those scores might not even match up to each other. Or even the probabilities. The confidence of one classifier may be sort of absurdly high compared to one of the others. So regularization can sometimes help with this problem. But in general, it's sort of a disappointing way to actually work with this. Okay, so that said, it's not completely hopeless. There's actually some theory that goes along with this, which is that if the average error, say, of the k classifiers is epsilon, then we have that the multi-class error of the one versus all approach is less than or equal to k minus 1 times epsilon. So does that sound good? No, not so good. Why not so good?
Say if you have 1,000 classes.
Yeah, if you have 1,000 classes and your error is like 10%, uh-oh, then the multi-class error bound here is actually something much greater than 1. So, so this is a little bit disappointing. So the question is, can we actually do better? Okay, so a different decomposition that we could look at is that of all versus all. Okay, so let's just do a quick sketch of what all versus all looks like. So it's the same idea. This will be our reduction number 2 here. Okay, so in all versus all, we're going to build one classifier for each pair of classes. Okay, so so this is a little bit different. And it has a downside, which is it's one binary classifier per pair of classes. So how many actual binary classifiers then? K choose 2. Ugh. Okay, well that doesn't sound helpful. I mean, before at least we only had K classifiers. Now we have K choose 2 classifiers. And so if you were thinking about that same data set as before, right, where we have our blue examples and our red examples and our green examples, then here we could actually look at you know, the first classifier, which is going to look at just the blue points and the red points. And so the classifier that we learn here would be something like, we could subscript our W here with blue and red to indicate that it's just learning to classify the difference between those two. And then we could learn a separate classifier that just does, say, the blue and the green points. And here, we're going to have one more, which is to differentiate the red and the green. And so at the end of the day, in this sort of tiny example, we actually have the same number of binary classifiers that we learned to accommodate 3 classes. Okay. But as the number of classes grows, this is going to end up growing pretty rapidly. So what would we say prediction actually looks like? So we could actually, again, sort of translate our classifiers, these 3, back to our original data set. And so we would have one classifier here, which is, we'll give a different looking color here. So this is the red versus blue. This is the blue versus green. And the red versus green. So now we have these 3 classifiers. And again, we're going to want to do some sort of voting between these classifiers. So this time, what should our voting actually look like? How can we piece this together into something that will actually make predictions?
So each class take the k-1 classifiers to conserve this class and aggregate the scores and integrate.
Yeah.
Take arithmetics.
Right, so we could say that, so here, this is our W blue versus green. This is our W blue versus red. And this is W red versus green down in the corner here. And so, if we wanted to figure out what should be classified blue, we could say, well, everywhere that blue gets more votes than red and green. Okay. So here, where are the places where blue gets more votes than red and green? Maybe I should color these slightly different for you. I'm just going to give them arbitrary groups. So these colors now have no correspondence to the actual classifier itself, but now we can talk about them. So what's going to get classified as blue here? Okay, you guys seem unsure, so why don't you take a moment, talk to the person sitting next to you. Is this like too obvious or not obvious? I think not obvious. Okay, so why don't you talk to the person next to you. If it is incredibly obvious, then you can all just make jokes about how obvious it is. If it's not, then actually you should come up with an answer. Okay, go ahead.
The video
Do you know how long ago? So they can't see me. Oh.
Yeah, that's what I was saying. So like that line kind of, because you know that everything between VR and VR. Exactly. Yeah.
Okay, maybe I won't actually touch anything. And
Yeah. So yeah.
I think because like I'm not important to this video. Okay, I think let's just let it roll through.
That's the right.
So could you just let them know that?
Or no.
Yeah, we're aware.
Because you also have the. Exactly. Yeah. So the right of that makes sense.
Okay. So good discussion. How many of you think you have an answer?
So that wouldn't have any.
Okay, a handful of people. Good enough. Let's see. From among the people that have an answer, someone gonna get finished? Yeah.
So anything about the blue line and about the green line?
Would be blue, right? Because in this region, it should be the case that up here, this region is going to get 2 votes from blue and green. And this region is also going to get 2 votes from blue and green. But it's only going to get, let's see. Oh. Vote from, yeah, so it's only going to get 1 vote from this red classifier, and it's not going to get the vote from this red classifier. The same thing goes for green. So in this region, it's going to get the vote from this green classifier, but it's not going to get the vote from this green classifier. Okay, so here we're doing this sort of this voting scheme that's just sort of 0-1 voting, which again is kind of a foolish thing to do. I mean, after all, we have scores from these classifiers, and so if they're at all reasonably calibrated with each other, then hopefully we could do a little better by actually relying on those scores. Okay, so it turns out then that we can also make sort of a simple theoretical statement about this one, which is sort of if the average binary classifier, or the average binary error of the k classifiers is epsilon, then the multi-class error of all versus all, AVA, is less than or equal to 2 times k minus 1 epsilon. Still not very good. Yeah, question.
If those like the line will intersect on the same point.
So in this case, I kind of drew them in such a way that they did. They don't necessarily need to, and we could actually have like a funny gap in the middle.
And that region is actually tied, right?
Yeah, exactly. So you can't actually see that region in my picture here. Okay, so this is bad. In fact, this is worse than our original idea. Okay, so the question is, can we do anything better than this? You know, it just sort of feels so disappointing. I mean, we had this one decomposition that didn't really get us anywhere. We had this other decomposition. It seemed like, you know, maybe it was going to work out, but then, you know, it doesn't really give us much better theoretical guarantees. So, okay, on to our third reduction here. Oops. And our third reduction is going to be for a classification tree. And a classification tree is kind of a simple idea. Okay. So suppose we're just going to jump straight to an example for this one because these are simple enough that I think the example is actually going to make them clear. Let's suppose that the number of classes we have is 8. Okay. And in that case, our tree could be something like this. So at the root node, it's going to try to divide whether our new instance is from the left set of labels or the right set of labels. Okay. Oops. Okay. And we could actually say then that the classifier that does this will label it as H0. Okay, so this is a classifier that takes in an X and just tells us whether it's going to be from this set or that set. Okay. So if it goes down the left branch, then we're going to have another classifier that tries to tell us whether it's from the set 1, 2 or from the set 3, 4 on this side. And on the other side, whether it's from the set 5, 6 or 7, 8. And to actually get those classification decisions, we're going to need 2 more classifiers, H00 and H01. Okay. And so H00 is going to further subdivide into 1 versus 2, and 3 versus 4, and 1 versus 2 will tell us whether it has label y equals 1 or y equals 2. And 3 or 4, whoops, I guess we need a classifier name down there. So 1 versus 2 is going to be H000, and this will be y equals 1 versus y equals 2. And then 3 versus 4, we'll say the classifier there is 0, 0, 1. And it gives us y equals 3 versus y equals 4. And then the tree is going to keep going on the other side in exactly the same way. So here we'll have 5 versus 6, and 6 versus 7. And we'll have classifiers like H010 and H011. And these will give us y equals 5, 6, 7, and 8. All right? So now, what we've done is we've decomposed this classification problem with 8 labels into a collection of 7 classifiers. Okay, so here's where things get interesting. We can actually get sort of more theoretical results here. And namely, if the average binary error is epsilon, then the tree classifier error is going to be less than or equal to log base 2 of k, or well, the ceiling of that, times epsilon. Finally, a mildly reasonable looking result. Okay, so how is it that we now got sublinear? Can anyone think of sort of a short proof that the tree classification error here would be log base 2 of k times epsilon? How could we show this?
is it something like as we go down the tree, the error gets reduced between only those two classes, something like that, along the line?
That's, so you should be thinking about, I'm used to chopping, but it stays in your hand much better. So you should be thinking about going down a tree, but here we want to be thinking about the length of the path and its impact on our potential for making error. So with that in mind, can anyone see how we could make sort of a proof sketch here?
So the height of the tree is log k.
Uh-huh.
So for each data, it will go up either way. Like from top to down, it will go through like log k binary classifiers.
That's right. So it's going to go through log k binary classifiers. And so the statement that we need is something about the tree classifier error in terms of those potential errors we could make.
Just for each example, consider the number of classifiers they need to experience before making a decision. So the previous two models, OVA or AVA, each example needs to experience like k minus 1, 2 times k minus 1 classifier, but this one only needs to experience 1k classifier.
Right, exactly. It's a question of how many of these binary classifiers need to be right in order for us to make a correct classification, right? So we could say that roughly the proof sketch is something like there are at most log base 2 of k classification errors that we could make, right? Right, this is the actual path length. And we would make each one with probability epsilon. Right? So if we're trying to predict y equals 3, there's epsilon probability that we make the mistake at h0. Now, from there, there's then epsilon probability that we make the mistake at h00. And then there's also epsilon probability that we make it at h001. And so in the end, we would say that the tree classifier error should be less than or equal to the sum of those epsilons. Yeah.
Are those epsilons the same for each way?
Oh, just because we assumed that they were. We didn't want to be here all day. We've got more important things to talk about. So let me make another note here. Here, there's really a key question that comes out of this. And that key question is, there are many possible trees. How many in terms of the number of labels? Polynomial or exponential in the number of labels? This is a question like, how many of you have heard of the Catalan numbers? Okay. No, I would think that's like standard fare in like 15251 around here. So there are exponentially many. The Catalan numbers are the number of parenthesizations of a sequence. And that's how many possible, that's related to the number of possible trees that we have here. So we could say, so which do we choose? Okay. So I'll leave sort of as an exercise to actually design something reasonable. But what's an intuition for how we might want to choose the labels on this tree? See if someone else has an idea here. Just an intuition. What would you want at the root node? divide into two groups of labels.
Two groups of labels where in which either one group the data points stay together, they're not too separated. So the first classifier will be the decision boundary won't be too complex.
Yeah, exactly, right? So you asked this question, why did we assume that all of the errors were the same along the way? Well, if we were the ones designing the tree, then we could actually choose the label sets such that the error at the top of the tree was as small as possible, right? Because if we have high error at the top, that's going to be bad for all of the other decisions that we subsequently make. So we could kind of take that intuition all the way through. Okay, so let's see. I'll leave as an exercise for you guys to actually sketch out sort of a picture corresponding to this. We'll skip that detail. Okay, so I want to talk about hierarchical classification. This is a different setting, and it comes up all over the place. So the setting is you're given a hierarchy over output labels, and we could say that otherwise this is the same as multi-class classification, because each leaf is just going to be a label. Okay, so this is the ImageNet data set, and one way that we could set it up would be that the leaves of this hierarchy over possible labels are the actual things that we care about. But we have this side information, which is that a hen and a nester and a nightbird and a bird of passage, these are all different types of birds, which are types of vertebrates, which are types of chordates, and so on. And so these labels actually live within a hierarchy. Okay, so it comes up other places if you're trying to say, work with a data set where you have pairs of occupation descriptions and then their SOC code. So this is a real problem that the CDC cares about. So the input text is something like rigging up man or mimeographer or doctor of optometry or wool presser, compressed machine operator. That might be a typo that they put in there. A pretzel packer. So I guarantee you that the words pretzel packer do not appear anywhere in the standard occupational classification, which is a hierarchy of codes. Okay. But if you're an epidemiologist, you actually probably want to study, what are the hazards that a pretzel packer faces in their day-to-day work. And so figuring out what code or what class of occupation they're in is important. So we could think of the label set in hierarchical classification as being the leaf nodes on this hierarchy. A tree is actually given to us. And so one way that we could actually solve hierarchical classification is by decomposing the actual multi-class classification problem into a sequence of, say, in this case, binary classification problems, where the decision of what the classification tree actually looks like is given to us by the hierarchy that somebody else conveniently already wrote down for us. Okay. So here's an important question. If you're doing hierarchical classification, does the hand-engineered hierarchy, say from the standard occupational classification or from ImageNet, does it actually give you a better classification tree than if you had come up with the tree on your own by some algorithm? Does anyone have any guesses for how this usually plays out in the real world?
Doesn't it depend, like sometimes if people create the hierarchy already, it's more understandable, but if you have like something that's more that's a model, you might have too fine-grained of a classification, so you might need to adjust.
Yeah, so it might be that the hierarchy is actually interpretable by a human, but that in feature space, the hierarchy is not actually making the decisions easier for you. And so often what people find is that it entirely depends on the particular task and the particular hierarchy that you're working with as to whether sort of a machine-generated classification tree or a hand-generated hierarchy is actually going to give you better results in the end. Okay? But what's fascinating about this is that it kind of exposes a possibility, which is that there's sort of a structure handed to you versus a structure that you could learn. And both of them might have different advantages. Okay. So, let's see. Okay, so error correcting output codes are sort of our reduction number 4. And what we could think about is that the tree classifier, we could write out sort of its behavior via a matrix, where we would say the matrix has rows corresponding to our labels. And let's say that the labels are A, B, C, and D. And we'd have some binary classifier for these, where H0 is going to divide up, say, A and B down one side of the tree, and C and D down another side. And then for the A and B labels, we're going to have H00, which is a classifier that divides A and B apart from each other. But it doesn't actually look at C and D at all. And then H10 is going to be a classifier that just looks at C and D and doesn't look at A and B. Okay, and so in this setting, we could actually use this matrix to conceptualize sort of how the tree classifier is functioning. Okay. This is just sort of a schematic representation of what it's doing. Okay, so I want to take that same schematic, and now I want to generalize it a little bit. Namely, we're going to say that we have our same label set, A, B, C, D, and now we're going to have classifiers like H0 that say divide A and B versus C and D. But then we're going to have an H1 that completely independently looks at dividing up into, say, A and C versus B and D. And then H2 is going to come along and it's going to have yet a different scheme, like maybe +1 here, -1 there, +1, +1. And H3 could be, say, +1, -1, -1, +1. And H4 could be +1, +1, +1, -1. So here the point is that in all of these cases, we're going to have these different classifiers that look at all the labels at once. And we know that you really only need 3 classifiers to get to get this decomposition into 4 labels. Okay. But we can just keep adding more and more classifiers here. Okay. So if we keep adding more and more classifiers, then what we're really doing is we're essentially saying that we're kind of going to assume these are actually noisy. And then we'll have these other classifiers that essentially allow us to have an ability to withstand more errors. Okay, so So I'll just give the punchline here. The error of error correcting output codes, we can say is less than or equal to 2 epsilon for that same epsilon that we've been talking about, the average binary error. Okay, and the best possible, you can also prove, is epsilon over 2. So what we're looking at is only 4x worse than optimal. So as well, maybe we should throw some homework questions on about this. You can think about how to capture those other reductions that we talked about as special cases of error correcting codes. Okay, so that we should definitely throw in. It's a lovely little exercise. Okay, so I think I started late, and so I'm going to impose 2 more minutes on you, past our usual ending point. So I want to just briefly mention sort of our punchline here, which is extreme classification. So imagine that you're building a facial recognition system. Okay, how many of you can actually recognize these 6 different faces? Anyone? Can anyone do it? I think we have Newell and Simon, or Simon and Newell. I actually, this is Longinus. We know Hinton and Turing and Hopper. These are all, incredibly important computer science, and many of them Turing Award winners. And yet, if you think about facial recognition, suppose you were trying to build a facial recognition system for everybody who was ever photographed. Gosh, how many people have been photographed since the invention of the camera? Probably billions, right? Okay, so extreme classification, the setting is that the output label set is extremely large, millions of labels. And otherwise it's the same as multi-class classification. Okay, it's just multi-class classification, but with huge numbers of labels. So there's all these example tasks. Large-scale facial recognition, predicting Amazon product categories or Amazon items, Wikipedia tags, Flickr image tags, language modeling. All of these have output spaces in the millions, or maybe more. So I want to highlight one algorithm for you, because this is just it kind of pulls together all these ideas that we've been talking about. So logarithmic one against sum, the idea here is that you build a recall tree where each leaf node contains a set of possible labels. Okay, but that set of labels, this is actually an example of a recall tree, is going to have size less than or equal to log base 2 of k. And the depth of the tree is going to be less than or equal to log base 2 of k. And so the idea here is that you can actually learn one binary classifier per internal node in this tree. And those are going to route you to one of these leaves. Okay, in the classification tree, when you get to the leaf, you just know what the label is. But here, when you get to the leaf, you get back a set of log k labels. And at that leaf, there is a multi-class classifier that predicts between that subset of the labels. So the idea here is that the recall tree is essentially filtering each instance down into a subset of sort of reasonable labels for that particular instance. And the power of this algorithm is that even on a massive label set, for one, it competes on sort of important benchmarks with the sort of standard one against all multi-class classification setup, like a big neural network that just gives you a softmax over the entire output vocabulary. But the speed is order log k in the number of labels, both at training time and at test time. Okay, so you don't even need to create a score for every possible output label. You only need to get from the root down to one of these leaves. That takes order log k binary classifiers. And then at that leaf, you're doing a order log k computation to choose among the log k possible labels. Okay, so the space is the same again as like the big giant neural network, where you have one output node, say per face, per billions of faces that you could possibly predict. Oh, and it also comes with the ability to do online learning. Okay, and so, on these sort of benchmark tasks, we find that it performs almost as well as one against all sort of the big standard like linear model or the big neural network, but it's dramatically faster. So here, this is showing the speed of one against all versus the logarithmic one against some, and this vertical axis is a logarithmic inference time. So it's logarithmically scaled. Okay. And so so this is sort of a beautiful place to end because it's taking all of these ideas that we had just looked at, and it's putting them together in this sort of fascinating way that allows us to really treat a huge multi-class classification problem as a structured prediction problem, where we're trying to find some path down to an appropriate leaf. We make a sequence of decisions through this recall tree to get back our set of possible labels. Right? So here, this example X came in, it could have gone left or right, it went left. Here, it could have gone of decisions followed by a multi-class classification problem. And so next time, we're going to pick up and think about how we could take sort of more complex structured prediction problems and treat them as a sequence of